The sun has a radius of 7 times 10 to the 8th meters and is a distance of 1.5 times 10 to the 11th meters from Earth. The surface temperature of the sun is 5,800 kelvins. Show that the intensity of the solar radiation incident on the upper atmosphere of the Earth is approximately 1,400 watts per square meter, right? What we're going to do here, and there's actually a formula for this. This is an astrophysics thing, which is sort of funny because it's, I don't know, it's just interesting to me that they put a question on there that is astrophysics, but there it is. What we're going to do here is we're going to figure out the power output of the sun, right? So the intensity is watts per square meter, right? Which means it's total power output divided by the area which it's spread over, right? Okay. And so if we're standing some distance from the sun, here's the sun, right? If we're some distance here from the sun, that brightness that it's going to be, the intensity of it is going to be the power output divided by, and the area is 4 pi r squared, right? That's the area of the surface of a sphere. So what we're saying is that if we're some distance from the sun, whatever the power output that sun has, right, is going to be spread, that's the watts, right? It's going to be spread out over how many square meters are on the surface of the sphere that is a radius equal to the distance we're standing from that star. Okay, this is a basic thing, and it's actually in the data packet. It's D1, and it's the third formula, right? Which is just L divided by 4 pi d squared. But I'm not going to confuse things. Let's just go power divided by 4 pi r squared, right? And the power is going to be for a star. The power will be the power emitted by some hot object, right? This is thermal radiation. So that's going to be E. We'll use a 1 for our emissivity. We'll assume that the star is perfectly emissive, right? And then the Stefan Boltzmann constant times the area times the temperature, to the fourth, right? And here's our temperature. It's 5,800, so you plug 5,800 into there. The area of the surface of the sun is going to be 4 pi r squared, right? And the radius of the sun is this, right? That'll be your r. So plug that in for that, right? 4 pi r squared. Notice that there's like a 4 pi that will cancel if you put it on there. And then Stefan Boltzmann, look it up. I think it's 5.67 times 10 to the minus 8. That's in the front of the packet, okay? So look that guy up. So that'll be your numerator, will be just 1 times the Stefan Boltzmann constant times 4 pi r squared, and that's the radius of the sun, and then times the temperature of the sun to the fourth, right? And then when we figure out the intensity out at the Earth's distance, we need to divide that power over the sphere, the giant celestial sphere, okay? And so that this r is that, right? Okay. And when you do it, I got like 1397.4 when I did that. But anyway, good luck. All right. Let's see. The albedo of the atmosphere is 0.3. Deduced that the average intensity over the surface of the Earth is 245. And so what you're going to do is, the first thing is that 30% gets reflected, right? So take that number and multiply whatever the answer is here, right? Multiply by 1 minus 0.3 or 0.7, right? And that's how much makes it through the atmosphere. Right, but then there's the concept of the Earth is receiving energy over an area that is circular, right? But it's being spread out over a sphere. So we need to multiply that by the ratio of the surface area of a circle divided by the surface area of a sphere, right? So a circle is pi r squared. Be sure to show this too. You need to show that it's area, that you're not just, I'm going to divide by 4 for some random reason, right? Okay. You need to deduce. Okay. And then the area of a sphere is 4 pi r squared. And obviously the pi r squareds cancel, and you're multiplying by a factor of 1/4. And this accounts for like day and night, and the fact that the poles don't receive light at the, at a 90-degree angle or something like that. It's always a glancing angle. So it's the average, right? We're averaging night and day or whatever, okay? And then estimate the surface temperature of the Earth. Well, you're going to get some answer here, right? That it's 245 watts per square meter. That's our radiant energy per square meter, right? So what we can do is we know the power radiated by the Earth is E. We'll use 1 again for E. Okay, and then sigma area times temperature to the fourth, right? But notice that that's watts per square meter. So if you do power per area, that is watts per square meter, the area cancels out of this thing, right? So what you're going to do is you're going to take this power over area, which is 245, right? 245, and that's going to equal just E, which will be 1, sigma, which will be, sigma, and temperature to the fourth, okay? And you'll get a temperature of the Earth. I got one between 250 and 260 kelvins, okay? And then the final question says, the average surface temperature of the Earth is much warmer than the temperature you'll calculate here, right? Okay. Suggest how the greenhouse effect helps explain the difference between the temperature estimated in C and the actual temperature of the Earth, right? And I think really very few people understand the greenhouse effect, so it's worth talking about a little bit here, right? We have an atmosphere. Here's the Earth, right? It's surrounded by this nice little blanket that's greatly exaggerated by this diagram, right? So here's our Earth, right? And what you got to understand is that what's coming in from the sun, the incoming radiation is short wavelengths. The atmosphere is transparent to short wavelengths, right? But if it contains greenhouse gases, and we've got to mention greenhouse gases, right? Okay, if it contains greenhouse gases, it allows short wavelength to pass, but it blocks, it absorbs, so it's transparent to short, and it blocks or absorbs long wavelength, okay? Okay, so the short wavelengths are on the average of 700 nanometers or so can get through the atmosphere. It warms the Earth. The Earth is not nearly as warm as the sun, right? The sun is at 5,800 kelvins. The Earth is at 288 or something like that, right? Okay, so this is re-radiating in the infrared range, right? And those infrared, those long wavelength waves, this is like short wavelength, right? Those long wavelengths are absorbed by the atmosphere, right? So the emitted radiation is in the infrared long wavelength, low frequency region, right? That we need to say that. The greenhouse gases, some kind of gases in the atmosphere absorb that infrared radiation. They allowed the short wavelength to go through, but they absorb infrared, right? That radiation is radiated in all directions, including out into space, right, and sideways in all these directions. But some of it is radiated back to Earth, and that warms the Earth. Okay? All right.